Right now, 26,000 light-years away, our galaxy's core is running physics experiments that no textbook fully explains. Stars orbit something they should not survive. A wall stops the fastest particles in the universe. A gamma-ray glow has gone unidentified for 15 years. And somewhere buried in the crowded center, an object nobody has identified switches its radio signal on and off with no detectable rhythm. This is not distant ancient history. This is happening right now, and the signals are still coming in. In 1933, a young engineer named Carl Jansky was hired by Bell Labs to track down interference-disrupting transatlantic radio calls. He built a rotating antenna mounted on wooden wheels in a field in New Jersey. It looked like a carnival ride made of pipes. He spun it slowly, pointing it at different sections of the sky, listening for the crackle of electrical noise from distant storms. He found the storms, but he also found something that would not behave. A signal that came back every single day, shifting slightly with each sunrise, as if it were tied not to anything on Earth, but to something fixed in the sky. After months of careful tracking, Jansky confirmed it. The signal was not coming from a storm. It was coming from the center of the Milky Way galaxy. He published his findings, and the scientific community barely noticed. In 1933, most astronomers cared about visible light. Radio waves from the sky seemed like a curiosity, not a priority. Jansky moved on, and his discovery sat nearly untouched for a decade. Then a plumber-turned-amateur scientist named Grote Reber built a dish antenna in his backyard in Wheaton, Illinois, and picked up the same signal himself. He mapped the whole sky in radio waves. The brightest point on the entire map was a single compact location, dead center of the galaxy, in the constellation Sagittarius. Not a star, not a nebula, something that was screaming in radio waves, while remaining completely invisible to optical telescopes, hidden behind a curtain of gas and dust so thick that visible light could not pass through it at all. The implication was clear and unsettling. Whatever sat at the center of our galaxy was producing enormous amounts of energy. Enough energy that it outshone everything else in the radio sky across 100,000 light-years of stars. And nobody could see it directly. That gap between what was being heard and what could be seen would drive decades of investigation. And the answer that eventually emerged was stranger than most astronomers had imagined. Before getting into what actually lives at the galactic center, it helps to understand how difficult it was to even determine where the center is. We are inside the galaxy. Measuring the distance to its center from here is like standing in the middle of a crowded forest and trying to accurately estimate the forest's total size. Dust and gas obscure the view in every direction. Stars overlap each other. Everything is in motion, including the platform you are measuring from. The first serious attempt was made by the astronomer Harlow Shapley in the early 20th century. He noticed that clusters of old stars were not spread evenly around the sky. They clumped in one direction. He used that asymmetry to triangulate the center. His estimate placed the core at roughly 50,000 light-years away. Significantly off, but the direction was correct. By 1985, the International Astronomical Union, the official governing body for astronomical standards, locked in a distance of 27,700 light-years. That number went into textbooks. It became the foundation for calculations about galactic structure, the sun's orbital period, and the positions of neighboring star clusters. It stayed in place for 35 years. Then, in 2020, a Japanese radio astronomy collaboration called VERA produced the most precise map of the Milky Way that had ever been attempted. Their measurement revised the distance to 25,800 light-years, a difference of almost 2,000 light-years from the official figure. 2,000 light-years sounds like an abstraction. To make it concrete, light travels about 6 trillion miles in a single year. 2,000 light-years is 12 million trillion miles. The error in humanity's map of its own galaxy was that large. The same data set revealed a second surprise. The sun is moving around the galactic center faster than previously measured. The old estimate was about 136,000 miles per hour. The new measurement puts it closer to 150,000 miles per hour. We are moving faster through the galaxy than the textbook said, and we are closer to the center than they said. Both numbers affect every model that depends on our precise position. If humanity was off by 2,000 light-years on something as basic as our own address in the galaxy, the lesson is worth sitting with. Every map of the cosmos is an approximation. Every baseline number carries a margin of uncertainty, and some things sitting much closer to us than 2,000 light-years have been even harder to identify and understand. The galactic center itself remained essentially invisible until infrared telescopes gave astronomers the ability to see through the dust. Infrared light passes through gas and dust clouds that completely absorb visible wavelengths. When researchers pointed infrared instruments at Sagittarius A, they could finally watch the stars living near the core directly. What those stars were doing was immediately surprising. The stars closest to the galactic center were moving extraordinarily fast, not gently drifting, the way stars in the quiet regions of the galaxy do, but racing, curving, looping in tight elliptical orbits. The orbital speeds required a massive gravitational anchor, pulling everything toward a single compact point. Two independent research teams, one based in Germany at the Max Planck Institute, and one operating out of the United States at UCLA, spent over a decade tracking the same group of stars using different telescopes, different instruments, and different analysis methods. They never directly coordinated their results. They both arrived at nearly identical conclusions. The object pulling those stars into their tight orbits had a mass of roughly 4 million times the mass of our Sun, and it fit inside a region smaller than our solar system. There is exactly one thing in known physics capable of packing 4 million solar masses into a space that small. A supermassive black hole. The German team measured 4.15 million solar masses. The American team came in at 4.3 million. The convergence from two independent groups using completely different data is one of the strongest forms of scientific confirmation that exists. The two lead scientists, Andrea Ghez and Reinhard Genzel, shared the Nobel Prize in Physics in 2020 for this work. But here is the part worth sitting with. A black hole does not emit light. You cannot photograph it the way you photograph a star. What Ghez and Genzel proved was the black hole's existence entirely through the behavior of things around it. The object itself remained hidden. They found the whirlpool and concluded there must be a drain at the center. Even though the drain was invisible, the black hole was confirmed through absence. The most closely tracked star in this cluster is called S2. Its orbit takes about 16 years to complete, making it one of the fastest orbiting stars ever recorded. At its closest approach to the black hole, S2 travels at nearly 3% of the speed of light. That is roughly 20 million miles per hour. A commercial airliner flying at full speed would require approximately 40 million years to cover the same distance S2 covers in a single second. At that speed, in that gravitational environment, the effects predicted by Albert Einstein's general theory of relativity become directly measurable. When S2 swings close to the black hole, its light shifts slightly toward the red end of the spectrum. Gravity is so intense at that distance that it literally stretches the light waves as they leave the star. Scientists detected this gravitational redshift with high precision during S2's closest pass in 2018. The measurement matched Einstein's predictions almost exactly. That was a live test of general relativity in one of the most extreme gravitational environments in the known galaxy. It passed. In 2020, the relativistic precession of S2's orbit was confirmed. Einstein's theory predicts that in a strong gravitational field, an elliptical orbit does not stay fixed. The ellipse itself slowly rotates over time, like a drawing being gradually spun on a turntable. S2's orbit shifted by a small but measurable angle after one full trip around the black hole, exactly as general relativity predicted. Together, these measurements represent some of the strongest verifications of Einstein's theory ever performed, in conditions far more extreme than anything producible in the solar system. But other stars in the same cluster showed behavior that did not fit as neatly. Small deviations in their orbits, tiny wobbles that the standard model of a single central black hole in an empty environment could not fully account for. Scientists proposed several candidates: hidden intermediate mass black holes orbiting alongside the main one, dense concentrations of dark matter clustering near the core, or simply the irreducible uncertainty of tracking objects 26,000 light-years away through clouds of interfering gas. None of those explanations has been confirmed. None has been ruled out, and then there are the 6 objects sitting even closer to the black hole than any of those stars. Objects that move like stars but look like gas clouds. Objects that should have been destroyed. Objects that survived. In 2004, a team tracking infrared sources near the galactic center noticed something anomalous. Among the fast-moving stars orbiting Sagittarius A, one object stood out. It moved like a star, following a clean orbital path, but it looked like a gas cloud. Fuzzy at the edges, extended. warm in a way that a free-floating gas cloud so close to a supermassive black hole should not remain for long. They catalogued it and moved on. Then they found another. And another. Today, 6 of these objects are confirmed in the same region. They are called G objects. The first 2 discovered were named G1 and G2. Their orbital periods range from 170 years for the shortest to 1600 years for the longest. The environment immediately surrounding Sagittarius, a star, is one of the most hostile in the galaxy. The black hole's gravity at close range is powerful enough to rip a gas cloud apart through a process called tidal disruption. Imagine holding a water balloon and pulling it from both ends until the tension snaps it into droplets. That is what gravity does to a diffuse object that passes within reach of 4 million solar masses. The G objects pass within reach. They should emerge as scattered debris. They come out intact. The discovery that forced everyone to take this seriously happened in 2014. G2, the second of these objects to be found, was approaching the closest point in its orbit. Astronomers around the world scheduled observation time. Papers were published predicting the outcome before it happened. The models were specific. G2 would pass within about 130 astronomical units of the black hole. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. G2 was heading within 12 billion miles of a 4 million solar mass black hole. As G2 approached, telescopes tracked it in infrared. The object began to stretch exactly as predicted. By early 2014, it had elongated visibly, its leading edge being accelerated faster than its trailing edge by the difference in gravitational pull across its length. Astronomers watching the live data saw exactly what the model said should happen. Then the leading edge swung around the black hole and started heading back out, and G2 followed it. Over the following months, the elongated shape began to contract. The tail caught up with the head. The expected bright flare of infalling gas never came. The dramatic increase in radio and X-ray emission that would signal a feeding event never arrived. Sagittarius A barely registered. G2 had survived. The scientific community processed this in stages. First came attempts to explain it away. Maybe the main debris had not reached the black hole yet. Maybe the flare was delayed. Astronomers watched for several more years. Nothing came. Then came the harder admission. The models were wrong. G2 contained something the pure gas cloud model could not account for. The leading theory today is that G objects are the products of binary star mergers. A binary star system is simply 2 stars orbiting each other. These are common throughout the galaxy. Roughly half of all stars in the Milky Way are thought to travel in pairs. In calm regions of the galaxy, binary pairs can orbit each other for billions of years without merging. But the galactic center is not calm. The black hole's gravity exerts enormous tidal influence on everything nearby. When a binary system drifts too close, the difference in gravitational pull between the 2 stars becomes strong enough to push them toward each other over time. Their orbits tighten. They spiral inward. Eventually, they collide and merge. When 2 stars combine, the result is a bloated, expanded stellar body surrounded by a thick shell of ejected gas and dust. From the outside, this merged object looks like a gas cloud. It glows at warm temperatures in infrared. Its edges are diffuse, but inside that shell, the merged stellar core is still there, dense enough and massive enough to resist being torn apart by the tidal forces that would shred a pure gas cloud. Think of it as a hard-boiled egg wrapped in cotton. The cotton looks soft and disperses under tension, but the egg inside holds together. The G objects, under this theory, are binary stars that merged sometime in the past few thousand years, still wrapped in the leftover material from their collision. As they continue orbiting the black hole, they will slowly shed that outer gas shell. Over tens of thousands of years, the merged core will be exposed and look like an ordinary star in an extraordinary orbit. Andrea Ghez and her team at UCLA published work supporting this merged binary model after the G2 event. The expected size, temperature, and behavior of a recently merged binary matched what telescopes observed. But this is still a theory. No telescope has directly imaged a stellar core inside any G object. The dust around them is too thick, the objects too far away, the galactic center too cluttered with competing sources for the view to be clear. 6 objects surviving where survival seems impossible, with the mechanism of their survival still technically unconfirmed. And that is not even the strangest feature of the galactic center. Something even more puzzling wraps around the entire central region from the outside. Invisible, maintained against all physical intuition, and blocking the rest of the galaxy from getting in. In 2020, data from the Fermi Large Area Telescope confirmed something nobody had predicted. The central molecular zone, the massive reservoir of gas and dust surrounding the galactic core, is nearly empty of cosmic rays arriving from outside. This requires some explanation, because the finding goes against everything the standard models predicted. Cosmic rays are not a type of light. They are actual particles, protons, atomic nuclei, moving at speeds approaching the speed of light. They are produced by exploding stars, colliding galaxies, and the violent environments near black holes. They travel freely through the galaxy in every direction, passing through open space, through star clusters, through nebulae. Almost nothing stops them. They penetrate nearly everything because the universe is mostly empty space and these particles barely interact with anything. The most energetic cosmic ray ever detected was a single proton carrying as much kinetic energy as a baseball thrown at roughly 50 miles per hour, compressed into a particle smaller than an atom. Physicists named it the "Oh my God" particle when they detected it in 1991. Ordinary cosmic rays carry less energy than that, but they are still moving fast enough that extended exposure to them in deep space is a genuine health risk. Astronauts traveling to Mars and back would receive a significant radiation dose from cosmic rays during the journey. These particles should be flooding the central molecular zone. The galactic center itself produces enormous quantities of cosmic rays from supernovae, from the activity of the black hole, from rapidly rotating neutron stars. Those locally produced particles flow outward freely, but particles arriving from outside the zone hit something at the boundary and stop. The Fermi telescope measured the cosmic ray density inside and outside the central molecular zone and found a sharp drop at the boundary. This is called a cosmic ray gradient, and it is steep enough to be unmistakable. The result is a one-way membrane. Things get out. Very few things get in. The boundary is real. The mechanism that maintains it is not confirmed. Two main theories compete. The first involves magnetic fields. The galactic center generates magnetic fields roughly 1,000 times stronger than the galactic average. The density of stars near the core is so extreme that in our part of the galaxy, the nearest star to the Sun is about 4 light-years away. Near the galactic center, stars are packed closely enough that neighbors might be separated by only a few weeks of light travel. That density means far more stellar activity, more stellar winds, more supernova explosions, more ionized gas, and far stronger magnetic fields. The magnetic barrier theory proposes that at the edge of the central molecular zone, these strong interior fields meet the weaker fields from the outer galaxy and compress into a wall. Cosmic rays are charged particles. They follow magnetic field lines. When they hit a compressed magnetic boundary, they get redirected. They curve away from the zone rather than penetrating it, like a river hitting a dam and spreading sideways rather than passing through. The problem with this explanation is that the measured magnetic fields at the boundary are not perfectly uniform. They show turbulence and structural gaps. A boundary with that much internal noise should leak. Some cosmic rays should find paths through. The measurements from Fermi suggest the barrier is sharper and more complete than a turbulent magnetic wall would produce. The second theory proposes something more active. The galactic center may not just be blocking particles passively, it may be blowing them away. The black hole, the massive stars, and the constant cycle of supernovae in the central region all pump energy into the surrounding gas. That energy drives a powerful outward wind, a stream of hot gas and particles flowing away from the core in all directions. This galactic outflow is a confirmed feature of the environment. If this outward wind is moving fast enough, cosmic rays traveling inward from the outer galaxy would have to fight the current, like trying to swim upstream in a fast river. Particles produced inside the central molecular zone would flow outward with the wind, accelerating as they go. Particles trying to enter from outside would be slowed, scattered, or pushed back before they could penetrate. This creates a directional effect. The wind acts as a one-way valve. This explanation accounts for something the magnetic field theory struggles to explain. The barrier is not uniform. The cosmic ray gradient is steeper on certain sides of the central molecular zone than others. A purely magnetic barrier would tend to be more consistent around the boundary. A wind-driven barrier would naturally vary depending on the wind speed and direction at different points around the zone. The data fits better. Neither theory fully accounts for all the observations. Both may be partly right, with magnetic compression and galactic wind working together to maintain the barrier. The wall stands. The reason it stands is still being debated, and the energy being produced inside that wall is generating a glow that has been the source of one of the biggest arguments in modern astrophysics for 15 years. In 2009, the Fermi Large Area Telescope was scanning the galactic center when it detected something strange. A glow of gamma rays spreading outward from the core in every direction, smooth, uniform, and centered precisely on Sagittarius A star. Gamma rays are the most energetic form of light. A single gamma ray photon carries millions of times more energy than a photon of visible light. They are produced by nuclear reactions, exploding stars, and particle collisions at energies that dwarf what the most powerful accelerators on Earth can achieve. Finding a gamma ray glow at the galactic center was not surprising. The center is an extreme environment. What was surprising was the shape and the scale. This glow stretched roughly 5,000 light years in every direction from the core. It was spherical, consistent across all directions, and surprisingly smooth. The spectrum of the gamma rays, meaning the range of energies they carried, did not match any known galactic source. Scientists called it the galactic center excess. Behind that deliberately dry name is one of the most heated arguments in modern astrophysics. The excess produces gamma rays at a specific energy range, around a few 100 million electron volts. That energy level is highly significant because theoretical models of dark matter, built decades before this glow was detected, predicted that if dark matter particles collide and annihilate each other, the resulting energy release would produce gamma rays at almost exactly this energy level. Dark matter is the invisible substance making up roughly 85% of all matter in the universe by mass. It has mass, it exerts gravity, but it does not emit light, reflect light, or interact with normal matter in any way currently detectable, except through gravity. Every large galaxy is embedded in a vast halo of dark matter far larger than its visible stars. The center of a galaxy, where gravity is deepest, should have the highest concentration of dark matter anywhere in that system. If dark matter particles can collide and destroy each other when they meet, the galactic center is where that would happen most often in the Milky Way. And if it does happen, the energy released would come out as gamma rays, at exactly the energies the Fermi telescope was now detecting. The story of dark matter itself begins with a Swiss astronomer named Fritz Zwicky in 1933. Zwicky was studying a cluster of galaxies and measuring how fast individual galaxies moved within it. He applied basic physics. The orbital speed of objects around a gravitational center tells you how much mass that center contains. The faster the orbit, the more mass. The galaxies in the cluster were moving far too fast to be held together by the visible mass of the stars within them. If only visible stars contributed gravity, the cluster should have flown apart long ago. Zwicky proposed that large amounts of invisible mass must be providing extra gravity. The scientific community largely ignored him. Then, in the 1970s, an astronomer named Vera Rubin made the same discovery at the scale of individual galaxies. She measured how fast stars at different distances from galactic centers rotated. Physics predicts that stars far from the center, where most visible mass is concentrated, should rotate slowly, the same way distant planets in our solar system orbit the sun more slowly than inner ones. Rubin found the opposite. Stars at the outer edges of galaxies orbited just as fast as stars near the center. The rotation curves were flat when they should have been declining. The only explanation was a halo of invisible mass surrounding each galaxy, extending far beyond the visible stars, providing extra gravity that kept the outer stars moving fast. Since Rubin's work, dark matter has been confirmed through multiple independent methods. Gravitational lensing, where invisible massive structures bend light from objects behind them. The large-scale structure of the universe, where the pattern of galaxy clustering matches simulations that include dark matter and fails to match ones that exclude it. The cosmic microwave background, the ancient light left over from the Big Bang, whose detailed temperature patterns require dark matter to explain their shape. Dark matter is real. What it is made of remains completely unknown. The theoretical candidate most consistent with the galactic center excess is called a weakly interacting massive particle. Theoretical physicists proposed this kind of particle decades before the Fermi telescope existed. The mass range and interaction strength that would make these particles annihilate and produce the observed gamma ray spectrum are exactly what the theories predicted long before the observation was made. When a predicted phenomenon appears in the exact location, at the exact energy with the exact distribution that theory said to look for, that is called a smoking gun. But extraordinary evidence requires extraordinary scrutiny, and the scrutiny revealed a competing explanation that fits the data almost equally well, one requiring no new physics at all. The galactic center has been producing new stars, burning through them in supernova explosions, and accumulating stellar remnants for billions of years. Among those remnants are pulsars. A pulsar is the collapsed core of a massive star that exploded. When a star with roughly 8 to 20 times the mass of our Sun reaches the end of its life, it detonates. The core collapses under gravity, crushing electrons and protons together into neutrons. The result is a neutron star, an object roughly the size of a city, packed with more mass than the Sun. Some neutron stars spin very fast, up to several hundred rotations per second. As they spin, their intense magnetic fields sweep beams of high-energy radiation around like a lighthouse. When one of those beams sweeps across Earth, we detect a rapid, regular pulse. That is a pulsar. A specific class called millisecond pulsars spin the fastest. Having been accelerated by pulling material from a companion star over long periods, they are old, stable, and they produce gamma rays at specific energies. The gamma ray spectrum of a population of millisecond pulsars matches the spectrum of the galactic center excess closely enough that the two signals are very hard to distinguish. The galactic center's stellar density is high enough that binary star systems form regularly, providing the fuel source for millisecond pulsars. Some estimates suggest as many as 100,000 millisecond pulsars could be hidden inside the central molecular zone, each one individually too faint to resolve from Earth's distance, but collectively producing an emission that would look exactly like the smooth, spherically distributed glow that Fermi detected. Two explanations. Both produce the right kind of gamma rays. Both produce the right spatial distribution. Both are physically plausible. One would be the greatest discovery in scientific history, the first confirmed direct detection of dark matter. The other would be a remarkable but ultimately conventional feature of stellar evolution in a dense environment. The current data cannot choose between them. Researchers have spent over a decade trying to separate the two signals. One group used a statistical technique to show that the galactic center excess has the statistical texture expected from millions of faint point sources, supporting the pulsar explanation. A different group used a different method and argued the signal is consistent with truly smooth diffuse emission, which favors dark matter. Both groups used the same Fermi data and reached opposite conclusions. The difference came down to how they modeled the complicated background emission from the galactic center, which is one of the most cluttered regions of the sky for gamma-ray astronomy. Resolving individual pulsars would settle the argument. If telescopes could see distinct point sources of gamma rays inside the galactic center, each matching the signature of a millisecond pulsar, the pulsar explanation would win and the dark matter interpretation would die. Current telescopes cannot achieve that angular resolution at the distance of the galactic center. The next generation of gamma-ray observatories, currently in development, might have enough sensitivity to find them. If they do not find pulsars where models predict they should be, the case for dark matter annihilation strengthens dramatically. Looking at dwarf galaxies orbiting the Milky Way offers another test. These small satellite galaxies contain very few stars and almost no pulsars, but they contain a lot of dark matter relative to their total mass. If dark matter annihilation is producing the galactic center excess, those dwarf galaxies should show a proportional glow. Searchers have found hints, but no definitive detection yet. Until better instruments arrive, the galactic center excess sits in an uncomfortable position. Confirmed as real, unexplained as to origin, potentially the most significant discovery in the history of physics. Potentially a very large population of spinning dead stars. Both possibilities remain alive, and neither can be dismissed. Buried in the same crowded galactic center, surrounded by all of these unresolved questions, is something that fits none of the categories that have been described so far. Something that switches its signal on and off with no predictable schedule. Something that sends out radio waves unlike anything that has been catalogued. Before, astronomers discovered the signal in 2021 while surveying the galactic center with the Meerkat radio telescope array in South Africa. The signal came from a point source, a compact, localized object. It flickered, it pulsed, it produced radio waves with properties unlike any known source in the region. The team that found it gave it an informal nickname based on the lead researcher who first noticed it. They called it Andy's object. What makes Andy's object different from other variable radio sources starts with polarization. Radio waves, like all electromagnetic waves, oscillate as they travel. Normally, those oscillations happen in random orientations. Polarized radio waves all oscillate in the same plane or rotate in a consistent spiral pattern. Producing highly polarized radio waves requires a very specific environment. Specifically, a powerful, organized magnetic field that forces the oscillations into alignment as they are emitted. Andy's object produces radio waves that are almost completely polarized. Not partially, almost entirely. That level of polarization points to an extremely strong and coherent magnetic field at the emission site. Known sources of highly polarized radio emission include pulsars, magnetars, which are neutron stars with especially extreme magnetic fields, and jets from active black holes. None of those matches what Andy's object does. Pulsars pulse with clockwork precision. Their timing is so reliable that astronomers use them as cosmic clocks. Andy's object turns on and off with no predictable rhythm. It is active for a period, then vanishes completely, then returns. The gaps between active periods vary. The duration of active phases varies. No underlying clock has been extracted from the data. Magnetars do produce erratic signals, but they also produce X-ray bursts during active phases. Telescopes monitoring the Galactic Center for X-rays during Andy's object's active periods detected no matching X-ray signal, which rules out a standard magnetar the highly polarized radio waves from Andy's object carry. Information about what the signal passed through on its way from the source to Earth. As radio waves travel through ionized gas permeated by magnetic fields, the polarization angle rotates. The amount of rotation, a phenomenon called Faraday rotation, depends on the magnetic field strength and plasma density along the path the waves traveled. Scientists named this effect after the physicist who first described the underlying physics in a laboratory setting. The Faraday rotation values measured from Andy's object are among the highest ever recorded for any source in the Milky Way. This means the radio waves traveled through a region of exceptional magnetic field strength and plasma density. The Galactic Center is already known to host strong magnetic fields, but the Faraday rotation from Andy's object suggests the fields in its immediate vicinity are even more intense than the surrounding region. Something local to that object is amplifying or concentrating the magnetic environment. One possible explanation involves scintillation, the same process that makes stars twinkle in Earth's atmosphere. Radio waves traveling through the turbulent plasma of the Galactic Center can brighten and fade due to interference patterns. If Andy's object is a faint but constant emitter, the interstellar turbulence could cause its apparent brightness to swing from detectable to undetectable and back, creating the impression of an object switching on and off. This explanation has not been ruled out, but the degree of variation observed is difficult to account for through scintillation alone. The signal changes too dramatically. The polarization properties shift between active phases in ways simple scintillation would not produce. Another possibility involves accretion, the process of a compact object pulling material from a companion star or surrounding gas cloud. When material falls onto a neutron star or small black hole, it can produce bursts of radio emission. If Andy's object is accreting gas from an irregular supply, the radio signal would switch on when gas arrives and switch off when the supply runs dry. The Galactic Center is full of gas clouds and stellar winds, making this a plausible fuel source. Some researchers have proposed that Andy's object belongs to an entirely new class of radio transient, a category of object only recently beginning to be systematically catalogued. Several other unpredictable radio sources have been found in the past few years using sensitive new telescope arrays. Some researchers think these may be related, part of an emerging family of objects whose properties current models of stellar physics did not anticipate. The signal is real. The polarization is confirmed. The irregular timing is confirmed. The origin remains unknown. The object class is unidentified. And here is the aspect of that situation worth pausing on. All of the anomalies described so far exist in the same single location, a supermassive black hole surrounded by young stars that should not exist there. 6 objects that survive what should destroy them. An invisible wall that blocks the fastest particles in the universe. A gamma-ray glow with no confirmed source after 15 years of study. An unidentified object sending out irregular, highly polarized radio signals. Now step back from the individual mysteries and consider the structure of the region they all occupy. Pull back from the black hole and its immediate surroundings, and you enter a vast region of gas and dust surrounding the galactic core, stretching roughly 900 light-years across its longest dimension. Astronomers call it the central molecular zone. The distance from Earth to the nearest star, Proxima Centauri, is about 4 light-years. The central molecular zone is over 200 times wider than that. It contains roughly 60 million solar masses of gas, enough raw material to build 60 million stars the size of our Sun. This cloud hosts an unusually rich chemistry. In most regions of the galaxy, ultraviolet light from nearby stars breaks apart complex molecules faster than they can form. The central molecular zone operates under different conditions. The high density of gas provides shielding from ultraviolet light in many regions. The cosmic ray barrier changes the ionization environment. The turbulence driven by the black hole's gravity and the dense stellar population stirs the gas constantly, mixing material and driving chemical reactions that more peaceful regions cannot replicate. Scientists have detected dozens of complex molecules inside the central molecular zone, including ones that serve as precursors to amino acids, the building blocks of proteins. This does not mean life is forming at the galactic center. The radiation environment is far too hostile for biology, but it means the chemistry happening inside the zone is producing molecular complexity at a level that continues to surprise researchers. The galactic center is, among many other things, a natural chemistry laboratory operating under conditions found nowhere else in the Milky Way. The temperature of the gas in the zone is also far higher than in typical molecular clouds. Molecular clouds in the outer galaxy have temperatures close to absolute zero. The central molecular zone's gas sits at temperatures many times higher, driven by turbulence and the constant energy input from the surrounding environment. That elevated temperature affects how the gas moves and whether it can collapse to form new stars. Star formation inside the central molecular zone is surprisingly suppressed given how much raw material is available. The gas is there, the mass is there, but turbulence keeps the clouds stirred and prevents them from collapsing into new stars at the rate that the available material would predict. The galactic center has enough gas to form millions of new stars, but forms far fewer than expected. Understanding why is an active area of research. The energy produced in the galactic center does not stay contained. It escapes, and it escapes on a scale that is genuinely hard to process. Material ejected by supernovae, heated gas driven outward by the black hole's activity, stellar winds from the dense population of massive stars near the core. All of it flows outward at high speeds in every direction. This galactic wind carries heat, cosmic rays, and magnetic fields into the surrounding medium. The consequences of this energy export extend far above and below the galaxy itself, literally. In 2010, scientists analyzing data from the Fermi Large Area Telescope found 2 enormous structures ballooning out from the center of the Milky Way, one above the galactic plane and one below, perfectly symmetric, each one stretching roughly 25,000 light-years from top to bottom. Together, the pair spans about 50,000 light-years end to end. They are called the Fermi bubbles. To understand their scale, the entire visible disk of the Milky Way is about 100,000 light-years across. Each Fermi bubble is roughly half that length in height. If you could observe them from outside the galaxy, they would look like 2 enormous lobes attached to the center of a flat disk, like a peanut shape rotated sideways. From our position inside the galaxy, they extend far above and below us, covering a huge fraction of the sky when observed in gamma rays. The bubbles glow. They emit gamma rays and microwave radiation across their full extent. They are filled with energetic electrons, magnetic fields, and hot gas. The boundary between each bubble and the surrounding medium is surprisingly sharp. There is a defined edge where the bubble material stops and the quieter surroundings begin. That sharp edge indicates the bubbles expanded relatively quickly and have been maintained against diffusion. The origin of the Fermi bubbles is debated. The 2 leading explanations reflect the same basic question underlying many galactic center mysteries: the black hole or the stars. The black hole explanation proposes that Sagittarius A star went through a period of intense activity a few million years ago. During that active phase, the black hole consumed a large amount of material and launched powerful jets of energy along its rotation axis. Those jets plowed through the surrounding gas, creating 2 cavities that expanded outward and are now observed as the bubbles. Evidence from X-ray observations of the gas around the bubbles supports the idea that something energetic expanded outward from the center relatively quickly. The stellar wind explanation argues that the combined effect of millions of years of stellar winds and supernovae from the dense star population at the galactic center could gradually inflate similar structures without requiring a past-active black hole phase. Simulations show that sustained stellar energy injection into the galactic center over long time scales can produce bubble-like structures. Both models match the overall size and shape reasonably well. Distinguishing between them requires detailed analysis of the gamma-ray spectrum and polarization inside the bubbles, which ongoing observations continue to refine. What is certain is that the galactic center has been pumping energy outward for a very long time. Enough energy to inflate two structures, each the size of a small galaxy, hanging above and below the Milky Way like a permanent record of the core's past behavior. The Fermi bubbles are not a recent or temporary feature. They represent millions of years of accumulated energy output. That raises a question many people ask, and it deserves a direct answer. Is any of this dangerous to us? The galactic center is violent. It contains a supermassive black hole. It blasts cosmic rays outward. It has inflated two structures the size of small galaxies above and below the Milky Way. Radio signals broadcast from unknown sources inside it. Strange objects orbit its core. Gamma-ray glows fill its surrounding region. And Earth sits 25,800 light-years away from all of it. That distance is the answer to most of the concern. The cosmic ray flux at Earth's location includes particles that originated near the galactic center, mixed with cosmic rays from many other sources throughout the galaxy. The cosmic ray environment at Earth has been roughly constant throughout the history of complex life. It fluctuates, but no galactic center event in the past has been identified as causing a mass extinction through increased radiation. The Fermi bubbles extend above and below the galactic plane, but Earth sits in the galactic plane at a distance from the center that places it far outside the region directly swept by their edges. Flares from Sagittarius, a star, the sudden brightenings when material falls into the black hole, produce bursts of X-ray and radio emission. Even the largest detected flares have produced energy, outputs far below what would be needed to cause measurable effects at Earth's distance. The one scenario that astrophysicists consider over very long timescales involves Sagittarius, a star undergoing an extremely powerful episode of activity producing jets as energetic as those seen in the most active galactic nuclei in other galaxies. But active galactic nuclei of that power are associated with black holes consuming material at rates far higher than anything currently measured or geologically recorded for our galactic center. The honest answer is that the galactic center is spectacularly dangerous to anything near it. At our current distance, it is a source of scientific fascination, not physical threat. What it might do in the future is a different question. Sagittarius A star is quiet right now. Relative to the most active galactic nuclei observed in other galaxies, our black hole barely whispers. But the galactic center carries evidence that this has not always been the case. A few million years ago, something happened at the galactic center. The Fermi bubbles are the most dramatic evidence, representing an enormous release of energy from the core over a geologically short period. And more recently, in astronomical terms, the galactic center showed signs of an active period much closer to the present. X-ray and gamma-ray observations of gas clouds in the central molecular zone have revealed a phenomenon called a light echo. Some clouds in the region glow with X-rays at exactly the intensity and spectrum you would expect if they were reflecting a past X-ray flare from Sagittarius A star. By tracing the geometry of the illuminated clouds and calculating how long the light took to reach them from the black hole's position, scientists estimated the timing of the original flare. The result pointed to an event roughly a few hundred years ago in which Sagittarius A star was millions of times brighter than it is today. A major feeding event, a brief but powerful eruption. The evidence for it is the X-ray light that bounced off the gas clouds and only arrived at those clouds as the light front from the original eruption expanded outward. The clouds are currently illuminated. The source that lit them up has already gone quiet. What that quiet period will look like in the future is uncertain. The black hole flares regularly in X-rays, multiple times per day, with brightness jumping dramatically for short periods. What triggers these small flares remains incompletely understood. Most are probably caused by clumps of gas or plasma falling toward the event horizon. A much larger future eruption is consistent with what the historical evidence suggests. The galactic center cycles through active and quiet periods. The current quiet period could last for millions of years, or something large could fall into the black hole relatively soon. The gas cloud G2, which survived its close pass in 2014, left behind a stream of material that continues falling toward the black hole. As that material arrives over coming years and decades, it may trigger a detectable increase in emission. Scientists have monitored the black hole carefully since the G2 passage for signs of feeding-related brightening. Any future major eruption would send radiation outward in all directions. From Earth's distance and with our atmosphere as shielding, even a large flare would be scientifically spectacular and practically harmless. It would, however, rewrite understanding of how and when galactic centers become active. Beyond the immediate questions of what Sagittarius A star will do next, the galactic center serves as something unique in modern physics, a laboratory that the universe built without being asked. Every process that plays out across the cosmos has a place where it operates in its most extreme form. Stellar physics happens everywhere stars exist, but the most extreme stellar physics, the conditions where normal rules break down, happens near the galactic center. Gravity operates throughout the universe, but the most extreme curvature of space, the conditions where general relativity produces effects large enough to measure clearly, happens near a 4 million solar mass black hole. The galactic center has tested general relativity in ways that are impossible to replicate anywhere closer to Earth. The relativistic precession of S2's orbit, the gravitational redshift of its light, these tests push the theory harder than anything achievable in the solar system. If the theory fails at some extreme scale, the galactic center is one of the best places to find out. The physics of accretion, how mass falls onto a compact object and releases energy, operates at its most extreme near Sagittarius A star. Every flare, every quiet period, every measured variation in the black hole's brightness teaches physicists something about how matter behaves in the strongest possible gravitational fields. That knowledge applies throughout the universe, wherever black holes are consuming material. Plasma physics at the galactic center operates in magnetic field environments far beyond what any laboratory on Earth can produce. The processes that accelerate cosmic rays to near light speed, that organize magnetic fields into coherent structures, that drive the outflows and jets. All of these are happening in real time at the galactic center, and observing them directly provides data that theoretical models of plasma physics cannot generate on their own. The chemistry of the central molecular zone tests what molecules can form and survive under conditions. Unlike any other molecular cloud in the galaxy, the molecules found inside the zone reveal how chemistry adapts to extreme conditions, which has implications for understanding the chemistry that preceded the origin of life on Earth. The stellar evolution mystery, the paradox of youth where young hot stars exist in a region where their formation should be nearly impossible, tests models of star formation in conditions that no nearby star-forming region replicates. Whatever mechanism allows massive stars to exist so close to a supermassive black hole must also operate in other galaxies with dense cores. The galactic center does not just raise questions about one location. Each answer at the center illuminates processes happening at scales from individual particles to the structure of the entire universe. And right now, there is a great deal that still cannot be seen. Between Earth and the galactic core lies a nearly continuous curtain of gas and dust that absorbs visible light almost completely. The dust absorbs roughly 1 trillion times more visible light than the galactic center can send through. Visible light astronomy of the galactic center is essentially impossible from Earth's surface. Radio waves and certain wavelengths of infrared and X-rays pass through. That is how almost everything confirmed about the galactic center has been learned. But the dust absorption is wavelength dependent. It blocks some wavelengths more than others. The view is patchwork. Certain phenomena can be observed. Others remain hidden because they emit primarily at wavelengths the dust blocks. The innermost dynamics of Sagittarius, a star's immediate environment at the scale needed to test detailed accretion models, cannot currently be seen. The Event Horizon Telescope image revealed the shadow, but not the fine structure of the infalling material at the smallest scales. Higher resolution radio imaging could reveal this, and planned upgrades to the Event Horizon Telescope network aim to achieve it. The internal structure of the G objects is completely opaque. The merged binary cores, if they exist, sit behind dust shells thick enough to block even near-infrared telescopes. Longer infrared wavelengths can penetrate deeper into dust, but sacrifice angular resolution in the process. A space-based infrared telescope, optimized for long-wavelength high-resolution imaging, could potentially see inside the G objects. No such telescope currently exists. The galactic center excess debate cannot be settled until telescopes resolve individual gamma-ray point sources in that region. This requires either dramatically larger collecting area for gamma-ray telescopes or observations from a detector in space with angular resolution far beyond current instruments. Several next-generation observatories are directly targeting these gaps. The Cherenkov Telescope Array, currently being built in Chile and Spain, will provide unprecedented gamma-ray sensitivity in the energy range most relevant to the galactic center excess. Planned upgrades to the Event Horizon Telescope network will improve angular resolution of the core. The Square Kilometer Array, a massive radio telescope network under construction, will survey the galactic center in radio wavelengths at sensitivity levels dramatically beyond anything currently available. The galactic center is not hiding. It is broadcasting in every direction. The instruments to receive all of its signals are simply still being built. Step back from each individual mystery and look at them together. A supermassive black hole surrounded by stars that should not be there. 6 objects that survive what should destroy them. An invisible wall that blocks the fastest particles in the universe. A gamma-ray glow with no confirmed source. Random radio signals from an unidentified object. Subtle deviations in stellar orbits that the standard model cannot fully explain. An alternative theory suggesting the black hole might not even be what it appears. Every one of those anomalies could have an explanation. Some have strong candidate explanations. None has been definitively solved. The question worth asking is whether this concentration of mysteries in one location is expected or suspicious. In science, anomalies cluster around the places that are studied most intensely. The galactic center is the most observed region of the galaxy outside the solar system. Telescopes have pointed at it in every available wavelength for decades. The sheer volume of data collected from this one region vastly exceeds what is available for almost any comparable area elsewhere in the Milky Way. More data means more opportunities to find things that do not fit. Some fraction of the galactic center's mystery list is probably the result of observational bias. Look anywhere hard enough and you find anomalies. But some of the anomalies at the galactic center are properties of the environment itself. The extreme conditions, the proximity to a supermassive black hole, the density of stars, the intense magnetic fields, the enormous gas reservoir, genuinely do create physics that does not operate the same way elsewhere. The G objects exist because of the specific gravitational and stellar density environment near the core. The cosmic ray barrier exists because of the energy budget of the galactic center. The gamma ray excess exists because the dark matter density or pulsar density at the core is higher than anywhere else nearby. These are not artifacts of looking too hard. These are real physical features of a genuinely extreme environment. The pattern of anomalies reflects something specific about the galactic center. It is a place where multiple physical processes, each operating at or near its extreme limit, intersect. Gravitational physics at 4 million solar masses, magnetic physics at field strengths 1,000 times the galactic average, chemical physics in a molecular zone unlike any other, radiation physics in a region producing gamma rays, X-rays, and radio waves simultaneously from multiple overlapping sources. Each anomaly connects to the others. The cosmic ray barrier shapes the chemistry of the central molecular zone. The magnetic fields affect the G object's survival. The dark matter density underlies both the stellar orbits and possibly the gamma ray excess. Andy's object reveals the magnetic environment that the cosmic ray barrier requires. The galactic center is not a collection of separate mysteries. It is one deeply complicated system where each piece of the puzzle interacts with every other piece. The researchers who study it, who spend their careers analyzing individual components of this system, consistently describe the experience in similar terms. In published papers, the language is careful and measured. Phrases like unexpected, unaccounted for, inconsistent with standard models. In conference talks and informal conversations, the word that surfaces most often about the galactic center is humbling. Humbling is the polite version of afraid. Here is what those researchers actually know. The standard model of the galactic center, a supermassive black hole surrounded by a dense stellar cluster embedded in a molecular gas zone, should be able to explain the basic features of the region with known physics. And it does explain many things. The stellar orbits broadly match. The black hole mass is confirmed. The outflows are real and detectable, but the model fails consistently at the edges. The G-objects survive when they should not. The gamma-ray excess has no confirmed source after 15 years of study. The cosmic ray barrier has no confirmed mechanism. Andy's object fits no known category. The fast-moving stellar orbits carry residuals that the standard model cannot account for. The dark matter core alternative remains mathematically viable despite the Event Horizon Telescope image. Each individual failure could be a gap in data, a measurement uncertainty, a missing component that will eventually be found and plugged into the model. Scientists would be comfortable with that interpretation if the failures were isolated. They are not isolated. They cluster. They connect. They resist resolution, despite enormous effort and increasingly powerful instruments. What researchers are cautious about? What keeps some of them genuinely uncertain in a field that is usually good at narrowing down answers? Is the possibility that the galactic center is showing them the edges of known physics. The place where models that work everywhere else begin to break down, because the conditions are too extreme for the approximations those models rely on. General relativity works at the scale of orbiting stars near the galactic center, but its behavior at the scale of the event horizon, in the infalling plasma, in the immediate vicinity of the singularity itself, is untested. The quantum behavior of matter under those conditions is not described by any confirmed theory. Quantum gravity, the as-yet undiscovered framework that would merge general relativity with quantum mechanics, is exactly what would be needed to describe physics at the galactic center's most extreme scales. The dark matter problem is another edge. The galactic center is the most likely place in the galaxy to find evidence of dark matter's particle nature. If the galactic center excess is dark matter annihilation and current instruments simply cannot confirm it, the implication is that our detection capabilities are not yet adequate to answer one of the deepest questions in physics. What scientists are grappling with, stated plainly, is that the galactic center may be telling them something true about the universe, and they do not yet have the language to fully read it. That is not a failure. That is where science actually lives, on the boundary between what is understood and what is not. The boundary at the galactic center is wider than at almost anywhere else in the observable universe. If you find this kind of science as compelling as the researchers who spend their careers on it, consider subscribing. The next generation of telescopes will begin returning results in the coming years, and the answers they find will either resolve these mysteries or deepen them considerably. 25,800 light-years away, the center of our galaxy is running experiments that physics has not fully solved. Every telescope pointed at it is listening for answers. The signals keep coming, strange, polarized, unexpected, and not yet explained. The questions are real. The data is growing. The boundary is moving. But it is moving slowly, and some of what sits on the other side of it may require entirely new physics to understand. That possibility is not cause for alarm. It is the most honest description of what the galactic center actually is, a place that currently exceeds our explanations, and a target for some of the most ambitious scientific instruments ever planned. The history of every major scientific breakthrough follows a recognizable pattern. First, an observation that does not fit, then years, sometimes decades, of competing explanations that all partially work. Then a moment when the right tool, the right measurement, or the right perspective resolves the ambiguity. The galactic center is currently somewhere in the middle of that pattern. Multiple anomalies confirmed, multiple explanations competing. The resolving measurement not yet made. Consider how long some of the galactic center's mysteries have persisted already. Carl Jansky detected the radio signal from the galactic center in 1933. For 20 years, the source was not identified. For 4 more decades, the case for a supermassive black hole was argued, but not confirmed. It was not until the 1990s and 2000s that stellar tracking settled the question definitively. The history of the galactic center is a history of long waits between discovery and understanding. The galactic center excess has been studied for 15 years without resolution. The G objects have been observed since 2004, without their internal structure being confirmed. Andy's object has been monitored since 2021 without its nature being identified. The The cosmic ray barrier has been confirmed for years without its mechanism being explained. These are not new mysteries. They are established anomalies that have resisted sustained effort by the best instruments currently available. That resistance is informative. It means the answers are not going to come easily or cheaply. They will require either dramatically improved instruments, entirely new observational strategies, or in some cases, possibly new theoretical frameworks. The next generation of telescopes represents the best current plan for obtaining those answers. Whether the plan works depends on whether the anomalies respond to better sensitivity and resolution, or whether they represent something that even better instrumentation cannot resolve without new physics. The distinction matters. Most scientific mysteries are resolved by better data. When a measurement is uncertain, more precise instruments narrow the uncertainty. When a source is too faint, a larger collecting area detects it. When two explanations make predictions that differ only slightly, higher resolution separates them. Most of the galactic center's mysteries should respond to this kind of improvement. The pulsars, if they exist in the numbers models predict, will become detectable with next-generation gamma-ray telescopes. The G object's internal structure, if it contains a merged stellar core, should become visible with a sufficiently capable infrared instrument. Andes object's mechanism should become clearer as more active periods are monitored with detailed polarimetry. But the orbital deviations of the fast-moving stars near the galactic center, the residuals that do not fit the standard black hole model, may be pointing at something that better stellar tracking alone cannot resolve. If the deviations reflect a genuine population of intermediate mass black holes, those objects will need to be confirmed through independent methods, including gravitational wave detectors. If they reflect a dark matter density enhancement, the only way to confirm that is through the gamma-ray signal, which brings the argument back to the galactic center excess. Everything connects. The galactic center is not a collection of isolated puzzles. It is a single complicated system being observed from the outside through a curtain of dust, with instruments that are good but not yet good enough, using theories that work well in most environments but have never been pushed to these extremes. The physicists who study general relativity use the galactic center as their most demanding test environment. The astrophysicists who study stellar evolution use it as a case study in physics near black holes. The cosmologists who study dark matter use it as their most promising detection target. The radio astronomers who study transient objects use it as the most densely packed source of unusual signals in the sky. The astrochemists who study molecular complexity use it as their most extreme laboratory. All of these communities look at the same region of space and find it relevant to their deepest questions. That convergence is not coincidental. The galactic center is where multiple extreme physical processes intersect, and each of those processes touches the most fundamental questions in its field. The galactic center excess is not just an astrophysics problem. If it is dark matter annihilation, it is the central problem in particle physics, because it tells you what dark matter is made of and how it interacts. The G objects are not just a stellar evolution problem. They are a gravitational physics problem, because they tell you how matter behaves in the tidal environment near a supermassive black hole. Andes object is not just a radio astronomy problem. It is a plasma physics and magnetic field problem, because its polarization reveals the magnetic environment of the galactic center's most extreme region. Scientists working across different fields are paying attention to the galactic center because whatever is happening there has implications that extend far beyond one region of one galaxy. If dark matter annihilates at the galactic center, it annihilates in every other galaxy too. If a new class of radio transient exists near the galactic center, similar objects may be scattered throughout the universe, previously unrecognized, because no one was looking carefully enough. If the orbits of stars near Sagittarius A require physics beyond general relativity, the implications cascade through every astrophysical calculation that uses the theory in strong gravity regimes. The stakes, in other words, are not just about understanding the center of our galaxy. They are about understanding fundamental physics in conditions that Earth-based experiments cannot reproduce. The Event Horizon Telescope image released in 2022 was a landmark. For the first time, humanity had a direct image of the shadow of a supermassive black hole in our own galaxy. That achievement required a decade of instrument development, novel algorithms, and coordinated observations across 8 observatories on multiple continents. The image confirmed the black hole's existence, its mass, and the basic prediction of general relativity about the size and shape of its shadow. But the image also revealed the limits of what is currently achievable. The shadow was resolved. The fine structure of the glowing material near the event horizon was not. The immediate environment of the black hole at the smallest relevant scales remains out of reach. The planned upgrades to the Event Horizon Telescope network, which will add more dishes on different continents and extend observations to shorter wavelengths, aim to improve the angular resolution by a factor of several. At the new resolution, the structure of the accretion flow close to the event horizon may become visible for the first time. That would allow direct comparisons between the observed structure and the predictions of competing theoretical models of black hole accretion. It would test whether the material near the event horizon behaves as general relativity predicts, or whether deviations are detectable at that scale. Given that the galactic center is 4 million solar masses and only 25,800 light-years away, it is the ideal target for this kind of observation. The Milky Way's central black hole is both close, enough and massive enough to have its immediate environment resolved in a way that no other known supermassive black hole allows. Similar logic applies to pulsar searches in the central molecular zone. Pulsars near the galactic center would provide the most extreme tests of general relativity available. A pulsar orbiting close to Sagittarius. A star would experience gravitational effects thousands of times stronger than those experienced by S2. Its timing could be measured with extraordinary precision, and any deviation from general relativity's predictions would be detectable at sensitivities impossible to achieve anywhere else. Finding even a single pulsar close to the galactic center would be one of the most valuable discoveries in observational physics. Extensive searches have been conducted. None has been found yet. The dense plasma of the galactic center scatters radio waves, making pulsar timing difficult at the wavelengths most surveys use. New surveys at shorter wavelengths, where scattering is less severe, are ongoing. The Square Kilometre Array, when it reaches full operation, will survey the galactic center in radio wavelengths with sensitivity dramatically beyond current arrays. It may find the pulsars that previous surveys missed. If it does, those pulsars will immediately become targets for the most precise tests of general relativity ever attempted. Each generation of instruments has pushed the boundary of what is knowable about the galactic center. Jansky's rotating antenna revealed a radio source at the core. Infrared telescopes revealed the stars orbiting it. Nobel Prize-winning work revealed the black hole's mass through stellar tracking. The Event Horizon Telescope gave the black hole a face. The Fermi telescope revealed the bubbles and the excess. Meerkat found Andy's object. The next generation will push further again. The answers to the galactic center's mysteries are not fundamentally out of reach. They are just at the edge of what current technology can access. The instruments being built now are specifically designed to cross that boundary. What researchers expect to find is not guaranteed to match what they find. The history of galactic center science is a history of surprises. The G objects were not predicted. Andy's object was not predicted. The Fermi bubbles were not predicted. The galactic center excess was not fully anticipated. Each major discovery came not from a theory that said something should be there, but from a measurement that revealed something that was not expected. That pattern is likely to continue. The next generation of telescopes will produce surprises. Some of those surprises will resolve current mysteries. Some will create new ones. The boundary between the understood and the not understood will move, but it will probably not disappear. The galactic center is too complex, too extreme, and too rich with overlapping physical processes to be fully explained by any single observational campaign or theoretical framework. What makes the galactic center unique in all of physics is that it combines maximum extremity with maximum accessibility. It is the most extreme environment within observational reach, a 4 million solar mass black hole surrounded by conditions unrepresented anywhere closer to Earth, observable with instruments that can be built and operated within human timescales. That combination is rare. No other location in the observable universe offers the same convergence of extremity and accessibility. The galactic center is where humanity goes to ask the hardest questions it currently has the tools to address. The questions are genuinely hard. The tools are genuinely limited, but both are improving. The signals keep coming from 25,800 light-years away, strange and polarized and not yet explained. and the instruments being pointed at them are getting more sensitive, higher resolution, and more capable with each passing year. The center of our galaxy is not done surprising us. The evidence strongly suggests it is just getting started. To fully appreciate why the galactic center holds this privileged position in science, it helps to think about what it would take to replicate its conditions in a controlled laboratory. A particle accelerator that could produce cosmic rays at the energies seen near the galactic center would need to be many orders of magnitude larger than the Large Hadron Collider in Switzerland. The Large Hadron Collider is 27 kilometers in circumference. A machine capable of accelerating particles to the highest energies observed in galactic cosmic rays would need to be larger than the solar system. There is no serious proposal to build one. A gravitational test environment matching the conditions near Sagittarius, a star, would require placing a precision instrument at roughly the same distance from the black hole as S2 reaches at its closest approach. That distance is about 120 astronomical units, roughly 3 times the distance from the Sun to Neptune, from an object with 4 million times the Sun's mass. The gravitational acceleration experienced at that distance would be thousands of times stronger than anything in the solar system. No spacecraft could be sent there within any remotely near-term time. Horizon Dot, a magnetic field laboratory matching the galactic center environment, would require sustaining field strengths 1,000 times above the galactic average across a region hundreds of light years across. No technology on Earth or plausibly imaginable from Earth comes close to this. The plasma environment of the galactic center, with its combination of extreme temperature, extreme density, extreme magnetic field strength, and extreme radiation flux, is simply unreplicable in any ground-based or space-based facility. It exists at the galactic center and nowhere else within reach. This is the fundamental reason why the galactic center commands so much scientific attention, despite being 25,800 light-years away. It is not just an interesting region of space. It is the only available laboratory for certain classes of experiment. When scientists point telescopes at it, they are not just satisfying curiosity about one corner of the galaxy. They are conducting experiments that cannot be conducted any other way. The question of whether dark matter annihilates is not answerable in any ground-based laboratory, because dark matter does not interact with detectors in any confirmed way. Every direct detection experiment has returned null results. Every collider search has come up empty. The galactic center is the one place where dark matter density may be high enough that its self-interaction produces a detectable signal. If it does not produce a detectable signal there, nowhere else in the accessible universe will either. The question of whether general relativity holds in the strongest available gravitational field is not answerable from Earth's surface, because Earth's gravitational field is far too weak to produce measurable relativistic effects at the precision current theories require. The galactic center provides the strongest gravitational field currently accessible to observation, and the stars orbiting Sagittarius, a star, are instruments in a physics experiment of a scale no human hand could construct. The question of what mechanisms accelerate cosmic rays to near light speed is not fully answerable from the cosmic ray detectors on Earth, because by the time cosmic rays reach Earth, they have lost information about their origin. Observing the acceleration process directly requires watching it happen in an environment where it occurs efficiently. The galactic center is such an environment, and radio, X-ray, and gamma-ray observations of the region are the closest thing to a direct observation of cosmic ray production that astronomers have. Every major open question in fundamental physics has a thread that runs through the galactic center. Quantum gravity remains unconfirmed, but the conditions near the event horizon of Sagittarius A star are where quantum gravitational effects would first become relevant. The particle nature of dark matter is unknown, but the galactic center is where dark matter annihilation would be most detectable. The mechanism of cosmic ray acceleration is debated, but the galactic center is where acceleration happens most efficiently. The behavior of matter in extreme magnetic fields is not fully understood, but the galactic center hosts the most extreme magnetic environment in accessible space. This convergence is not an accident. Extreme physics is concentrated at the gravitational center of the galaxy because gravity itself concentrates everything there. Mass attracts mass. Over 13 billion years, the galactic center has accumulated the densest stellar population, the most intense magnetic fields, the largest reservoir of gas and dust, and the most powerful source of energy in the entire Milky Way, whatever physics operates at its limits, is doing so at the galactic center. That is why researchers who study almost any area of high-energy astrophysics or fundamental physics eventually find themselves looking towards Sagittarius A. It is where the universe is running its most extreme experiments, and it has been doing so for billions of years, indifferent to whether anyone was watching. Humanity started watching seriously in 1933 when Jansky's rotating antenna picked up a signal from a New Jersey field. In less than a century, the understanding of that signal has grown from a mysterious radio source of unknown origin to a confirmed supermassive black hole surrounded by exotic objects, wrapped in an invisible cosmic ray barrier, glowing with unidentified gamma rays, and broadcasting irregular signals from unclassified sources. The rate of progress has been remarkable. The depth of remaining mystery is equally remarkable. The next decade will likely produce more answers about the galactic center than any previous decade in history. The combination of next-generation gamma-ray telescopes, upgraded radio arrays, improved Event Horizon telescope resolution, and the square-kilometer array represents the most powerful observational campaign ever aimed at the galactic center. Each of these instruments targets specific gaps in current knowledge. Each was designed with the specific anomalies of the galactic center in mind. If even one of the major galactic center mysteries is resolved in the next 10 years, the implications will be significant. A confirmed dark matter signal would reshape particle physics and cosmology simultaneously. A confirmed new class of stellar object from Andes-type behavior would open an entirely new chapter in stellar astrophysics. A confirmed intermediate mass black hole near the galactic center would settle decades of debate about how black holes of that mass range form and migrate. A definitive measurement, resolving the cosmic ray barrier mechanism, would advance understanding of how galactic centers regulate the chemistry and star formation of their surroundings. Any one of these outcomes would be a landmark result. The galactic center may deliver several of them within the same decade, or it may deliver new anomalies instead of resolutions. The history of the region suggests that increased observational capability tends to reveal new complexity as often as it resolves existing puzzles. What is certain is that the signals will keep coming. The galactic center is not going quiet. Sagittarius A will continue to flare. The G objects will continue their orbits. Andes object will continue to switch on and off unpredictably. The gamma-ray glow will continue to resist clear identification. The cosmic ray barrier will continue to deflect particles at its boundary. The Fermi bubbles will continue to expand slowly above and below the plane of the Milky Way, and the telescopes will keep watching, pointing across 25,800 light-years of intervening gas and dust, receiving photons and radio waves and gamma rays that started their journey at the most extreme environment in the galaxy and arrived here carrying information about physics that no textbook has yet fully described. The center of the Milky Way is not a distant abstraction. It is a real place. It is the gravitational heart of the system that includes our sun, our planet, and everything that has ever lived on it. Understanding it is not a purely academic exercise. It is part of understanding where we are, what kind of universe we live in, and what the laws of physics actually permit at their most extreme. That understanding is incomplete. It will remain incomplete for some time, but it is advancing, measurement by measurement, telescope by telescope, year by year. And the view from the boundary of what is known, looking out toward what is not, has never been more interesting than it is right now. There is one more angle worth examining before stepping back from the galactic center entirely. The question of what it means for science that so many anomalies cluster in one location and resist explanation simultaneously. In the history of physics, there have been periods where a small number of unexplained observations pointed toward major theoretical revisions. The ultraviolet catastrophe of the late 19th century, where classical physics predicted that hot objects should radiate infinite energy at short wavelengths, was eventually resolved by quantum mechanics. The failure of Newtonian mechanics to account for the orbit of Mercury was resolved by general relativity. The inability of classical electromagnetism to explain atomic stability was resolved by quantum theory. In each of those cases, the anomaly was specific. One measurement, one prediction that failed. The resolution came from recognizing that the failure was not a gap in data, but a genuine failure of the underlying framework. The galactic center's anomalies are more numerous and more varied. They span different physical phenomena, different observational techniques, and different theoretical frameworks. Some of them have candidate explanations within known physics. Others do not. The question scientists are cautious about is whether the collection of anomalies reflects a collection of individual gaps, each solvable with the right data, or whether it reflects something deeper, a coherent signal that the current frameworks are systematically incomplete when applied to conditions this extreme. The honest answer is that nobody knows yet. The instruments needed to resolve the individual anomalies may or may not exist. The theoretical framework needed to make sense of them coherently may or may not require revisions to current physics. The Galactic Center will tell us eventually, through its continued observations. What is already clear is that the Galactic Center is the place in the observable universe most likely to produce surprises that matter for fundamental physics. Its combination of extreme conditions, observational accessibility, and accumulated anomalies makes it unique. Every year of observation either narrows the range of viable explanations or reveals new complexity that existing models cannot account for. Both outcomes are scientifically valuable. Both advance understanding in ways that no other target can replicate. The researchers who work on Galactic Center science are not working on the periphery of physics and astronomy. They are working at one of its most active frontiers. The questions they are asking are among the most fundamental questions that human beings currently have the tools to address. The answers they are working toward will matter beyond the Galactic Center, beyond the Milky Way, and beyond the current generation of scientists who are doing the work. Science at this frontier is slow. The anomalies are persistent. The instruments are limited by physics and budget and the practical constraints of building machines that have to work in space or on remote mountaintops or across international collaborations. Progress is measured in years and decades, not weeks. But the Galactic Center is patient. It has been running the same experiments for billions of years. The signals it is broadcasting have been traveling toward Earth for 25,800 years. The photons arriving in a telescope tonight left the Galactic Center roughly 25,000 years before the first modern humans drew on cave walls in Europe. By the time those photons were detected and analyzed and published and debated, the Galactic Center had already moved on. Whatever it was doing 25,000 years ago was not the end of the story. The Galactic Center is still active. It is still producing flares, still driving outflows, still accelerating cosmic rays, still maintaining its mysterious barrier, still hosting objects that should not survive and signals that cannot be explained. Whatever it will show us next is already on its way. The light is already traveling. The radio waves are already in transit. The gamma rays are already crossing the dust curtain between us and the core. By the time the next generation of telescopes is fully operational, some of those signals will have arrived. Some of the mysteries will have resolved. Others will not. And somewhere in the data, almost certainly, will be something nobody expected, something that was not in any model, something that points toward a question nobody thought to ask. That is what the Galactic Center has always done. It has never cooperated with the simplest available explanation. It has always contained more than predicted. It has always resisted complete description. And it has always, eventually, yielded something real, something measurable, something that changed the way the universe was understood. 25,800 light-years away, the center of our galaxy is waiting. The telescopes are watching. The questions are outstanding. And the answers, when they come, will be worth everything that was put into finding them. It is also worth considering the scale of the effort that has gone into understanding the Galactic Center over the past century, because that effort reflects something important about how science works at its best. Jansky's original discovery in 1933 required no large team, no major funding, and no specialized astronomical institution. He was an engineer at a commercial research laboratory, working on a practical problem, who noticed an anomaly in his data and followed it carefully enough to identify its source. The discovery required intellectual honesty, careful measurement, and the willingness to report a result that nobody was expecting, and that nobody immediately took seriously. Grota, Reber's follow-up in the late 1930s and early 1940s, required personal investment. He funded his own backyard telescope, built it himself, and spent years systematically mapping the radio sky. He was not affiliated with a university or a government program. He was an amateur scientist with the discipline and persistence to produce the first radio map of the Milky Way. By the time the serious push began in the 1980s and 1990s to track the stars near the galactic center, the scale of effort had grown enormously. The teams led by Reinhard Genzel and Andrea Ghez each required dedicated telescope access at major observatories, sustained funding over more than a decade, the development of new instruments and techniques including adaptive optics to compensate for atmospheric blur, and the intellectual commitment to stay focused on a single target year after year as other fields moved faster and produced results more quickly. That commitment was recognized with a Nobel Prize, but the recognition came after 30 years of sustained effort on a problem that was not guaranteed to yield the answer everyone hoped for. Black holes were theoretically plausible. They were not proven at the Galactic center until decades of careful data collection made the alternative explanations untenable. The Event Horizon Telescope project took this kind of sustained effort to an entirely new level, creating a telescope. The effective diameter of Earth required coordinating observatories across 5 continents, synchronizing them to atomic clock precision, shipping petabytes of data physically by aircraft because internet connections were not fast enough, and developing entirely new data processing algorithms to stitch the observations together. The result was achieved because hundreds of people across dozens of institutions in many different countries agreed to work toward a single goal over many years. The scientists searching for the galactic center excess, monitoring Andy's object, tracking the G objects, and mapping the cosmic ray barrier are all engaged in similarly sustained efforts. Each of these projects requires years of observation, teams of researchers with different specializations, instrument development that takes longer than any individual career, and theoretical work that often advances in isolation from observational data. Because the data needed to test the theories does not yet exist. This is what scientific progress at the frontier of knowledge actually looks like. Not quick breakthroughs and sudden revelations, but slow accumulation of evidence over years and decades, with occasional moments when enough data has been collected that a conclusion becomes unavoidable. The confirmation of Sagittarius A star's mass was such a moment. The Event Horizon Telescope image was such a moment. The confirmation of the Fermi bubbles was such a moment. The galactic center is currently waiting for its next such moment. The data is being collected. The instruments are improving. The theories are being refined. Somewhere in the accumulation of current and near-future observations, there is a point where one of the major open questions tips from uncertain to answered. When that happens, it will be the product of years of invisible work done by researchers who chose to spend significant portions of their careers on problems that were not guaranteed to yield results within their working lifetimes. That choice, made repeatedly across the Galactic Center research community, reflects something real about why science works. The people doing it are genuinely motivated by the questions, not just the answers. The Galactic Center is interesting because it is genuinely unknown. If it were fully understood, it would be less compelling. The mystery is part of what sustains the effort, and the mystery is genuine. The G objects are not a solved problem with a pending publication. The Galactic Center excess is not a resolved question waiting for final confirmation. Andy's object is not a known phenomenon with an unpublished explanation. The cosmic ray barrier is not a theoretical prediction awaiting observational verification. All of these are real open questions, with real competing hypotheses, and real uncertainty about which explanation, if any of the current ones, is correct. Living with that uncertainty is part of working at the frontier. Researchers in the Galactic Center field do not know if their current best theories are right. They know the observations, they know the constraints, they know which explanations fit and which do not, and they know that better data will eventually force a choice. What they do not know is what that choice will be, or whether the framework they are using will survive contact with it. That uncertainty is not a weakness. It is the most honest possible description of where the science currently stands. The Galactic Center is one of the most intensely studied regions of the sky. The data available from it vastly exceeds what is available for comparable regions elsewhere. And after all of that effort and all of that data, fundamental questions remain open. The most important thing that fact tells us is not that something is wrong with the way science is being done. It tells us that the Galactic Center is genuinely harder to understand than the current generation of tools can fully resolve. The region is not being misunderstood because of insufficient intelligence or effort on the part of the researchers studying it. It is being partially understood because it is genuinely complex, genuinely extreme, and genuinely at the edge of what current physics can describe. When the next generation of instruments comes online, some of that complexity will resolve. Some of it will not. Whatever remains will define the agenda for the generation of scientists after that. The Galactic Center will continue to be studied, and it will continue to be surprising, for as long as the instruments pointed at it continue to improve. That is not a discouraging conclusion. It is the most interesting possible situation for anyone paying attention to how physics actually advances. The frontier is real. The questions are hard. The tools are improving, and 25,800 light years away, the center of our galaxy continues to broadcast in every wavelength, patient and indifferent and full of information that human beings are only just beginning to learn how to read. There is one final dimension of the Galactic Center story that deserves attention, because it connects everything discussed here to a perspective that is easy to overlook when focused on the technical details of stellar orbits and gamma-ray spectra and cosmic ray barriers. The Galactic Center is the gravitational center of the Milky Way. Everything in the galaxy, including the Sun and everything orbiting it, moves in relation to that center. The Milky Way is roughly 250,000 light-years across in its full extent, including the outer reaches of its dark matter halo. The Galactic Center sits at the middle of all of that. It is the point around which everything else orbits. The Sun completes one orbit of the Galactic Center roughly every 225 million years, traveling at about 150,000 miles per hour through the galaxy. That orbit has been completed about 20 times since the Sun formed. Each time, the Sun has passed through different regions of the Milky Way, encountered different stellar densities, and moved through the wake of different galactic events. The Sun's history is a history of movement relative to the Galactic Center. The Milky Way itself is not isolated. It is part of the Local Group, a collection of galaxies bound together by gravity. The Local Group is part of the Virgo supercluster. The Virgo supercluster is part of the Laniakea supercluster, a structure so large that it contains the mass of roughly 100 million billion suns spread across 500 million light-years. All of these structures are themselves in motion, falling toward even larger concentrations of mass at scales that make the Galactic Center seem local. But within the Milky Way, the Galactic Center is home. It is the reference point around which everything in the galaxy is organized. Its gravity determines the structure of the disk. Its energy output shapes the gas distribution across thousands of light years. Its history of activity has left marks on the galaxy that are still visible today in the form of the Fermi bubbles, the light echoes, and the chemical composition of the central molecular zone. Understanding the Galactic Center means understanding where we live at the most fundamental level available to current science. Not just the address, 25,800 light-years from the core, 2/3 of the way toward the outer edge. In a minor spiral arm called the Orion Arm, but the nature of the gravitational environment that has shaped the Sun's path through the galaxy for the past 4.5 billion years. That path, traced through varying stellar densities, different cosmic ray fluxes, and the occasional passage through the spiral arms, may have had consequences for life on Earth. The cosmic ray environment at Earth fluctuates as the Sun moves through regions of different density. Periods when the Sun passed closer to the Galactic Center, or through denser regions of the galactic disk, may have produced different atmospheric conditions on Earth than the current environment. The connection between galactic dynamics and planetary habitability is a young field, but it builds directly on understanding the Galactic Center and the structure it imposes on the rest of the galaxy. The signals from the Galactic Center carry more than information about physics. They carry information about the history and future of the system that produced every living thing that has ever existed. Understanding those signals, resolving those mysteries, learning what the Galactic Center is actually doing, is one piece of a much larger project. The project of understanding where we are and how we got here. That project is ongoing. The Galactic Center will continue to be a central part of it. The questions will not all be answered in a single generation or with a single instrument, or even within the careers of the researchers currently working on them. But each measurement made, each anomaly resolved, each new question raised by better data brings the project forward. 25,800 light-years away, the center of our galaxy is running its experiments. The instruments are listening. The analysis is ongoing. And the story of what is happening there and what it means for everything else is still being written. If you found this journey through the Galactic Center's mysteries as compelling as the science deserves, consider subscribing. The answers, when they come, will be among the most significant discoveries in the history of science. And the path to those answers runs directly through telescopes pointed at a single bright point in the constellation Sagittarius, 25,800 light-years from here, where the most extreme physics in the galaxy continues to unfold. The universe does not make it easy to study its most extreme places. Every major advance in galactic center science has required overcoming a specific technical obstacle. Jansky overcame the assumption that radio waves from space were not worth listening for. Reber overcame the lack of institutional support by doing the work himself. Gez and Genzel overcame the dust curtain by switching to infrared. The Event Horizon Telescope team overcame the resolution limit of any single dish by connecting observatories across the entire planet. Fermi overcame the opacity of the galactic center to visible wavelengths by operating in gamma rays above the atmosphere. Each of these advances required identifying the specific obstacle, developing a technique to overcome it, and then executing that technique at scales and levels of precision that had never been attempted before. The pattern repeats for every generation of galactic center science, and the next generation is already following the same pattern. The cosmic ray barrier is blocked by the difficulty of measuring cosmic ray gradients with sufficient precision across the boundary of the central molecular zone. New radio arrays with higher sensitivity are being deployed to improve those measurements. The galactic center excess is blocked by the inability to resolve individual gamma-ray point sources at galactic center distances. Next-generation gamma-ray telescopes with larger collecting areas are being designed specifically to achieve that resolution. Andy's object is blocked by the irregular cadence of its emission and the paucity of data during active phases. Dedicated monitoring programs with Meerkat and successor arrays are providing continuous coverage to catch every active period. The obstacles are specific. The solutions are in development. The timeline is measured in years to decades, not centuries. The galactic center mysteries are not permanently beyond reach. They are at the edge of what the next generation of instruments can achieve. That is the most accurate summary of where the science stands. Not solved, not unsolvable, hard, specific, and approaching the point where the right measurements will force a resolution. The galactic center has been studied for less than a century, with instruments capable of doing it justice. The serious investigation began in the 1980s. The most powerful tools available for studying it are being built now. The era of real answers is just beginning. Whatever those answers turn out to be, they will have been earned by a century of increasingly careful observation, increasingly powerful instruments, an increasingly refined understanding of one of the most extraordinary environments in the observable universe. The center of our galaxy, 25,800 light-years away, still broadcasting, still surprising, still waiting to be understood.